our integration topic, and we've been having a look at example 28, 29. We had a look at repeated integration by parts, and again, a bit of a laborious process, particularly if you're going to have to do it not just two times, but if you're going to have to do three or four or five. And in many ways, if it's a polynomial, if there's a polynomial element to it, we can see from this example, for instance, that the integral of x cubed e to the x is actually going to require effectively three integration by part sequences, because we need to differentiate the x cubed to make it x squared, and then to an x, and then to a constant term each time we differentiate one level. So it's going to take three sequences of integration by parts in order to get one integral that we can work out. So in order to alleviate that, we can actually come up with a shortcut way, and we call this a tabular method. And it's good if you understand it. It's one of these things that when you look at it, you think, well, why don't you always do that? But in a way, it's also good to be able to do it the full proper way. So I'll show you what this method is. So we've got two parts to it. We've got the integral of x cubed e to the x. Now, previously we would normally think of applying u and v dash, and we can kind of think of that as we normally would. So if u is x cubed and v dash is e to the x, really what we're trying to do, instead of, you can write that down, but really we want to think about doing it something like this. We want to differentiate one column, and we want to integrate another. So I'm actually going to put these as two table column headings. So derivative and integral. So we put the u value in one column, and we put the v dash value in the other. And what we want to do is to differentiate this expression as many times as it takes to get to 0. So clearly our second element would be 3x squared, and then 6x, and then 6, and then 0. Okay? And then we can do the corresponding integration. So we've got e to the x, the integral of e to the x is e to the x, the integral of that, and so on. This one is fairly straightforward in that it's always the same. So in order to get the answer, if you think about how this works, we've got, although we don't normally write this for the tabular method, just to show you where we're going, it's uv minus the integral of u dash v. So in actual fact, here is uv, okay, because we've integrated it. It's the second level of the e to the x, and so that's actually uv. So what we do is we take that and we say, okay, that's the integral of, well, let's move it down a little bit. So uv is represented by this first kind of diagonal expression. So the integral of x cubed e to the x with respect to x is x cubed times e to the x. And then minus, we're subtracting this integral u dash v. Now, this is where it starts to get lost because we can't see the result. But the pattern goes that we then subtract from that the product of the first derivative and the second integration. So it goes minus 3x squared e to the x, because that's the pair that match up, plus the product of these two terms here, and minus the product of these terms here, plus c. So in actual fact, that's it. That's the answer. You could take a common factor of e to the x, but otherwise, that's it. So it's a very quick way of working out our answer using repeated integration by parts in a tabular form. Okay, so that's how we would use the tabular method to solve a repeated integration by parts. I've got another couple of practice questions up here. What I'm going to do, I'm just going to have you look at these. If you want to practice them, you can pause the video right just now, and then I'm going to go over the solutions quickly. So you're going to pause it here, try them, and then you can press start and watch if your solutions are the same as mine. Okay, so here we have question 1, integral of x cubed sine x with respect to x. We want to think about two particular columns. We want a derivative column, and we want an integration column. So here's our headings, and we're going to nominate, as we would normally if we were doing integration by parts, the polynomial expression that we're going to use as the derivative, and sine x we're going to integrate. So we differentiate the x cubed term until, just like we did in the previous example, until we end up with 0. At this time we're integrating sine x, so sine x integrates to negative cos x, negative cos x integrates to negative sine x, negative sine x integrates to cos x, and cos x integrates to sine x. And what we're then going to do is consider these products here with the arrows. We're going to start off with a plus, a minus, plus, minus, and we can say therefore that the integral of x cubed sine x with respect to x is equal to x cubed times negative cos x, and then minus 3x squared multiplied by negative sine x plus 6x times cos x minus 6 sine x plus the constant of integration, which we can tidy up a little bit here. It might take us a couple of lines just to we'll do it one step at a time. So we've got negative x cubed cos x plus 3x squared sine x plus 6x cos x minus 6 sine x plus c. And we could technically take a common factor of the cos terms and the sine terms separately. So we've got a cos x term and a cos x term. One's positive, so we'll start with that. So we've got 6x minus x cubed times cos x. And then the sine terms, we've got plus 3x squared sine x minus 6 sine x. So we could say plus 3x squared minus 6 sine x plus c. That's just a wee bit of housekeeping. Okay, certainly a lot easier than trying to do it the full way with all the repeated integration by parts. And secondly, we'll just bring this down below. If you've had a go at the second one. Now, that's the polynomial expression is to the power 4, which means we would have even more complex calculations to do. But this way, we can do it quite straightforward. So we've got the derivative, and we've got an integration. Again, the polynomial expression we'll keep as the derivative, and we've got e to the x here. Differentiate x minus 5 to the power 4 gives us 4 times x minus 5 to the power 3 multiplied by the derivative inside, which is just 1, so there's no additional multiplier. Then we've got 12 times x minus 5 squared, again times 1, and then 24 times x minus 5 to the power 1. And just watch this one, because technically, of course, that's 24x minus 120. So when we differentiate one more time, we'll end up with just the 24 from the constant term in front of the x. Okay. Each time we integrate, of course, we've just got e to the x. There's no real thought required for that. And then what we need to do is set up our pairs, plus, minus. So this time we've got four different calculations. In fact, we need to go one more because we have to get that to 0. Just as well I remembered, it has to go all the way down to 0 on your polynomial expression. So we'll have 5 expressions to put together. So let's see what we're doing. Integral of x minus 5 to the power 4 times e to the x is equal to x minus 5 to the 4 e to the x minus, well, I'll tell you what, it looks like there's always going to be a common factor of e to the x, isn't there? So let's just do it right from the start. So it's just going to be x minus 5 to the power 4 e to the x minus 4 times x minus 5 to the power 3 times e to the x as your common factor, plus 12 times x minus 5 squared multiplied by e to the x minus 24 times x minus 5 times e to the x plus 24 e to the x plus c. Okay? Technically, we could simplify just maybe the last part of that if you really wanted to, because you get minus 24x minus 120 plus 24, so it become minus 96. But at the moment, we'll just leave it like that. So that's, again, another way to do a repeated integration by parts using a tabular method. It's quite a nice technique to be able to learn.